Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about critical loads of a cross-section. In the previous classes, we have learned that there are two types of beam. One is called a laterally supported beam and another is called a laterally unsupported beam. The laterally supported beam is supported at the compression flange, and when it is subjected to a load, it deflects only in the vertical direction. Whereas laterally unsupported beam actually deflects vertically slightly and then also deforms in the U direction laterally, and then it is also twisting by an angle gamma. And the laterally supported beams are governed by strength, whereas laterally unsupported beams are governed by stability. The equation for laterally supported beams is given by M equal to beta sub B into Zp into Fy, which means that it is failing through yielding, whereas the laterally unsupported beam M is equal to beta sub B into Z sub P into F critical B. F critical B refers to the critical buckling stress, and hence the failure mode is lateral torsional buckling for laterally unsupported beams. Irrespective of cross-sectional shape of open section, all the laterally unsupported beams exhibit three deformations U, V and gamma. Here you can see four different cross-sections. The first one is a doubly symmetric cross-section, and which is the only cross-section where the shear center and the centroid coincides, whereas for the rest of the cross-section, which is unsymmetrical eye sections as well as singly symmetric channel sections as well as the angle sections, the shear center and the centroid do not coincide, as you can see from the picture. So far we have learned that the concentrically loaded columns exhibit deformation only in single plane, which is U or V. What happens if we use the open sections for columns? Do they still fail by flexural buckling alone? Something we need to understand. Let us consider a thin-walled open cross-section of arbitrary shape as shown in the figure. Let x and y directions are assumed to coincide with the principal axis of the section, and z direction is along the longitudinal axis through the shear center O. The coordinates of the centroid C are denoted by x0 and y0. Upon application of load at centroid, the section deforms due to buckling. The deformation consists of a combination of bending about two transverse axes and twisting about the longitudinal axis. So the first one, as you can see, is flexural buckling about y axis. The next one is flexural buckling about x axis, and third one is the torsional buckling about the z axis. So the combination of flexural buckling and torsional buckling leads to what is known as flexural torsional buckling. How do we obtain the critical load for each of these buckling modes? We know that for flexural buckling, P critical is pi square EI by KL the whole square. Whereas what is P critical for torsional buckling and what is P critical for flexural torsional buckling? We can find a solution using the energy method, which is pi equal to U plus V. So this energy method for beams leads to elastic critical moment MCR, and for columns it leads to elastic critical load PCR. For simplification, we can reduce the deformations into two categories. The first one is pure translations. So there is translation in X and translation in Y, and then there is a pure rotation which is rotating about Z. For flexural buckling, the first translation is bending about Y axis or minor axis. The next one is bending about X axis or major axis, followed by torsional buckling where it is rotating about Z axis, that is the longitudinal axis, as you can see from the figure. The total potential energy of the member is pi equal to U plus V. Let us look at U, which is the strain energy due to buckling. So we can see that there is a potential energy when it is bending about Y axis or minor axis. Here U1 equal to half into 0 to L EIY into U double dash the whole square into dz. The next one is bending about major axis, and here U2 is given as half into 0 to L EIX into V double dash the whole square into dz. The first two components represents the flexural buckling. Then we have the torsional buckling where U3 is given as half into 0 to L GJ into gamma dash the whole square plus half into 0 to L EIW into gamma double dash the whole square into dz. So when we sum all of the stuff, we have U1 plus U2 plus E3, which is a big equation as shown in the screen here. Next is the potential energy due to external loads. So we have a column which is subjected to axial load. It is compressed. Upon application of axial load, the column undergoes transverse bending. Delta B is the distance by which the ends of the member approach one another as a result of transverse bending. And as shown in the figure on the left hand side, delta B represents the actual shortening of the column. From figure, we can observe that delta B is equal to the difference between the arc length S and its chord length L. So if the cross-sectional area of the fiber is dA, and the load at supports is sigma into dA, then the potential energy of the load acting on the fiber is given as minus delta B into sigma into dA. So, determining the axial shortening due to bending delta sub B, let us consider a fiber AB along length of column whose coordinates in the undeformed state are x and y, as you can see in the picture on the right hand side. So, consider a small element dz of the fiber along AB. After deformation has taken place, the x and y displacements of the lower end of the element are u bar and v bar, and the corresponding displacements at the upper end are u bar plus du bar plus v bar plus dv bar. This is pictorially shown here on the right hand side of the screen. From Pythagorean theorem, the length of a differential element of arc ds is given as ds equal to root of du bar the whole square plus dv bar the whole square plus dz bar the whole square. Multiply and divide with dz on the right hand side. We have ds equal to 1 plus du bar by dz the whole square plus dv bar by dz the whole square, the whole power half. Upon integrating the left side of the equation from 0 to s and the right side of the equation from 0 to L, we have 0 to s ds equal to 0 to L 1 plus du bar by dz the whole square plus dv bar by dz the whole square, the whole power half into dz. So, now s equal to 0 to L 1 plus half into du bar by dz the whole square plus dv bar by dz the whole square. Now, s equal to L plus half into 0 to L du bar by dz the whole square plus dv bar by dz the whole square into dz. Now, when we take the L to the other side, we have s minus L equal to half into 0 to L du bar by dz the whole square plus dv bar by dz the whole square into dz. Well, delta B is given as s minus L. So, delta B is equal to half into 0 to L du bar by dz bar the whole square plus dv bar by dz bar the whole square into dz. Now, the translations u bar and v bar of a fiber whose coordinates are x and y is equal to the translations of the shear center u and v plus the additional translation due to the rotation of the fiber about the shear center. The translation of the shear center u and v is a fixed value. And what about the translation due to rotation of the fiber about the shear center? Now, let us find out that. So, from the figure we can see that the point P moves to P dash. The P forms an angle of alpha at the coordinates x and y, and when it moves to P dash, we have an additional gamma, it rotates and it forms an arc length r. The differential displacement is given as A in the x direction and B in the y direction. So, let us find the additional translation due to the rotation above the shear center. From the figure on the right hand side, we can take this small triangle AB, P and P dash, which has an arc length as well as the chord length. It makes an angle alpha, as you can see on the right hand side. Now, this can be represented here in the small figure as well, and if that is alpha, the remaining angle is 90 minus alpha, and if that is 90 minus alpha, the other angle, as you can see here, that is closer to P dash is also alpha. From geometry, we have the length of the hypotenuse equal to r gamma from the figure on the right hand side. Sin alpha equal to A by r gamma, which means that A equal to r gamma into sin alpha. Similarly, cos alpha equal to B by r gamma, which means that B equal to r gamma into cos alpha. Now, from the figure, we can also deduce that sin alpha equal to y by r, which implies y equal to r into sin alpha, and cos alpha equal to x by r, which implies x equal to r cos alpha. Now, we can substitute y equal to r sin alpha and x equal to r cos alpha in the above equation. When we do so, we have A equal to gamma into y and B equal to gamma into x. Now, u bar is given as u minus A and v bar is given as v plus A, as you can see from the figure. So, which means that u bar is u minus y into gamma and v bar equal to v plus x into gamma based on the values of A and B that we have derived below. Now, substituting these values in delta sub B, we have the equation half into 0 to L d of u minus y gamma divided by dz the whole square plus d of v plus x gamma divided by dz the whole square into dz. Now, that is given as half into 0 to L du by dz minus d of y gamma by dz the whole square plus dv by dz plus d of x gamma by dz the whole square into dz. We can use the a plus b the whole square equal to a square plus 2ab plus b square and a minus b equal to a square minus 2ab plus b square. these two equations we can use and we can expand this equation further. When we expand this equation further, we get a big equation for delta sub B, as you can see in the screen. Now, substituting delta sub B in the potential energy due to external loads V, which is given as V equal to minus integral A of delta B into sigma into dA. So, when we substitute these values, we get a big equation for V. The ones that are highlighted in red color are the terms corresponding to delta sub B. Now, replacing the values in V using the equations given, which is integral of A into dA is equal to A, and integral of A into YdA is equal to Y naught A, and integral of A into XdA equal to X naught A, and integral of A into X square plus Y square into dA equal to R naught square into A. So, when we substitute these, replacing the values in V, we can further simplify the V equation, as you can see here, and finally we get V equal to minus P by 2 into a big equation that you can see on the right hand side. Now, substituting U and V in the total potential energy of the member pi equal to U plus V, we have another big equation of pi which consists of more than 7 terms. Now, substituting U and V in the total potential energy of the member pi equal to U plus V, we get a big term of pi which consists of 9 terms. Note, since U is very much greater than V, the deflection along the transverse bending, the term half into 0 to L EAX into V double dash into dz is ignored for beams. However, since both U and V are out of plane displacements and are equally large for columns, it is not ignored. Therefore, every term in pi contributes to the total potential energy of the column. Approximations are given here. U equal to C1 into sin pi z by L, V equal to C2 into sin pi z by L, and gamma equal to C3 into sin pi z by L. Now, the derivatives are very simple, as we have seen in the previous classes. U dash equal to C1 into pi by L into cos pi z by L, U double dash equal to minus C1 into pi by L the whole square into sin pi z by L, V dash equal to C2 into pi by L into cos pi z by L, and V double dash equal to minus C2 into pi by L the whole square into sin pi z by L. Gamma dash equal to C3 into pi by L into cos pi z by L, and gamma double dash equal to minus C3 into pi by L the whole square into sin pi z by L. Now, let us check if the boundary conditions of the member are satisfied by these equations. The lateral displacements are given as at z equal to 0 and L, U and V are 0. So, U equal to C1 into sin pi z by L, at z equal to 0, U equal to 0, and then at z equal to L, U is also 0. Now, similarly, V equal to C2 into sin pi z by L, at z equal to 0, V equal to 0, and at z equal to L, V is also 0. Now, for bending, M equal to EIY into d square U by dz square, which is equal to EIX into d square V by dz square is equal to 0. At z equal to 0, L, the bending curvature d square U by dz square and d square V by dz square is equal to 0. So, which means that d square U by dz square equal to minus C1 into pi by L the whole square into sin pi z by L, which is equal to minus C1 into pi by L the whole square into sin pi of 0 by L, which is equal to 0. Similarly, when we substitute z equal to L, we again get 0. Similar thing happens for d square V by dz square as well. So, for z equal to 0 as well as z equal to L, both the values are 0. Now, for twist at z equal to 0, L, gamma equal to 0, gamma is given as C3 into sin pi z by L. So, at z equal to 0, gamma equal to 0, and at z equal to L, again gamma equal to 0. Now, for lateral bending, MF is given as EIW into d square gamma by dz square equal to 0. M sub F represents the lateral flange bending, which is given as EIW into d square gamma by dz square, which is equal to 0. So, at z equal to 0 on L, the twistature, which is defined as d square gamma by dz square, is equal to 0. As you can see, when we substitute z equal to 0, it is 0. Similarly, when we substitute z equal to L, again it is becoming 0. So, the approximation satisfies the boundary conditions of the member. We have U equal to V equal to 0, and also d square U by dz square equal to d square V by dz square is equal to 0. Similarly, gamma equal to 0 and d square gamma by dz square is also equal to 0. Now, let us evaluate pi by using the approximations U, V and gamma. Evaluating each integral in pi, we have half into 0 to L EAX into V double dash the whole square into dz. When we substitute the value of V double dash, which is minus C2 into pi by L the whole square into sin pi z by L, we can simplify this further and we get the equation EIX by 4 into Ct square into pi power 4 by L cube is equation 1. We do the same thing for equation 2. So, we have this half into 0 to L EIY into U double dash the whole square into dz. We substitute the values and we simplify this further. We have EIY by 4 into C1 square into pi power 4 by L cube, which is equation 2. The equation 3 is half into 0 to L EIW into gamma double dash the whole square into dz. When we substitute gamma double dash, we can further simplify these equations and finally we get EIW by 4 into C3 square into pi power 4 by L cube, which is equation 3. Now for half into 0 to L Gj into gamma dash the whole square into dz, we have the equation which is further simplified as Gj by 4 into C3 square into pi square by L, which is equation 4. Now equation 5 is given as P by 2 into 0 to L du by dz the whole square into dz. So when we do so, we have minus pi by 2 into 0 to L C1 into pi by L into cos pi z by L the whole square into dz. We need to understand this minus value comes from the above equation for pi, where there is a minus p by 2 on the outside of the brackets, which when multiplied comes inside the bracket, and hence we have this minus term. Now when we simplify this further, we have minus p by 4 into C1 square into pi square by L, which is equation 5. Now p by 2 into 0 to L 2 into y naught into du by dz into d gamma by dz into dz, which is equation 6. We simplify this further, we have pi by 2 into y naught into C1 into C3 into pi square by L, which becomes equation 6. Now the seventh term is minus p by 2 into 0 to L r naught square into d gamma by dz the whole square into dz. When we substitute d gamma by dz, which is C3 into pi by L into cos pi z by L, and simplify this further, we have minus p into r naught square by 4 into C3 square into pi square by L, which is equation 7. Now equation 8 is given as minus p by 2 into 0 to L dv by dz the whole square into dz. So when we substitute this further, we get minus p by 4 into C2 square into pi square by L, which is equation 8. The last equation is the equation 9, which is minus p by 2 into 0 to L 2x naught into dv by dz into d gamma by dz into dz. So we substituted, we simplify this further and we get the simplified form, which is minus p by 2 into x naught into C2 into C3 into pi square by L, which is equation 9. All the equations 1 to 9 has been listed on the left hand side of the screen. Substituting these integrals in pi, we get a big equation here. Now we can club these equations in a logical form and then we can simplify this further. We are now replacing the terms py equal to pi square EIY by L square and px equal to pi square EIX by L square and p gamma equal to 1 by r naught square into Gj plus pi square EIW by L square. So when we do so, we get a simplified equation for pi. And now using the principle of stationary potential energy, for equilibrium, the total potential energy of the system pi should be 0. So which means that del pi equal to 0. Now the critical moment is reached when the neutral equilibrium is possible. The requirement for neutral equilibrium is such that the partial derivative of pi with respect to three constants, which is C1, C2 and C3, must vanish. So now let us do del pi by del C1 equal to 0. So we get a big equation here. When we simplify this further, we have pi square by 4L into 2C1 into Py minus P plus 2Y0 into P into C3 equal to 0. So which gives rise to the equation C1 into Py minus P plus Y0 into P into C3 is equal to 0, which is equation 1. Similarly, del pi by del C2 equal to 0. We simplify this further. When we do so, we have C2 into Px minus P minus x0 into P into C3 is equal to 0, which becomes equation 2. Now del pi by del C3 is equal to 0. We get a big equation. We simplify this further. Then now we have C3 into R naught square into P gamma minus P plus Y0 into PC1 minus x0 into P into C2 is equal to 0, which becomes equation 3. Now all the three equations are listed here, which can be represented in the form of a matrix. Now we have this nice neat matrix representing these equations, and for a non-trivial solution, the determinant should be equal to 0. The determinant of the matrix is given as a big equation in the screen, and we can simplify this further. The roots of equation gives critical values, hence replacing P equal to P critical, we have this equation R naught square into Py minus PCR into Px minus PCR into P gamma minus PCR minus P critical square into x naught square into Py minus PCR minus P critical square into y naught square into Px minus PCR is equal to 0. Now the roots of this cubic equation are critical loads of this cross section, which is the intent of this lecture. Now we have several cross sections here. How do we obtain the critical load for each of these cross sections is the question. Now x0 and y0 are defined as the distance between the shear center and centroid along the x and y axis respectively. So for a doubly symmetric sections, we can see that the shear center and the centroid coincides, and also for point symmetric sections, the shear center and the centroid coincides. In such situations, x0 equal to y0 equal to 0. So when we substitute x0 equal to y0 equal to 0 in the above cubic equation, we get Py minus Pcr into Px minus Pcr into P gamma minus Pcr is equal to 0, which means that the roots of the above equations are Pcr equal to Py equal to pi square Eiy by L square, or Pcr equal to Px equal to pi square Ex by L square, or P critical equal to P gamma equal to 1 by R0 square into Gj plus pi square Eiw by L square. Now substituting the above roots in equations 1, 2, 3, the following information regarding mode shapes can be obtained. For the first row in the matrix, we have C1 into Py minus P plus Y0 into P into C3 is equal to 0. When we substitute P equal to Py or P critical equal to Py, C1 cannot be 0, and since there is no C2, C2 is obviously 0, and C3 must be 0 in order to satisfy this equation. This represents pure flexural buckling about y-axis. Since Pcr equal to Px here, C2 cannot be 0, and since C1 is not represented, it is automatically 0, and C3 must be 0 to satisfy this equation. This represents pure flexural buckling about x-axis. For Pcr equal to Py, C3 cannot be 0, and hence C1 and C2 must be 0 in order to satisfy this above equation. So this represents pure torsional buckling about z-axis. So this indicates that I sections and Z sections can either buckle by bending about one of the principal axis or twisting about the shear center. In these situations, the combined flexural torsional buckling does not occur for these cross sections, which is doubly symmetric cross sections as well as point symmetric cross sections. Depending on the shape and dimensions of the cross section, one of the loads given above will have the lowest value and will determine the mode of buckling for the members. So this is represented in AISC 360. As you can see here, the critical buckling stress is very similar to what we have derived here, which is pi square E divided by LC by R the whole square. So the Euler load is almost always the lowest buckling load. Now what if the cross section is simply symmetric? So here y0 equal to 0. Now substituting y0 equal to 0 in the above cubic equation, we get Py minus Pcr into R0 square into Px minus Pcr into P gamma minus Pcr minus Pcr square into x0 square equal to 0. So this equation is satisfied either if Py minus Pcr is equal to 0, which is the term outside the big bracket, or R0 square into Px minus Pcr into Py minus Pcr in minus Pcr square into x0 square equal to 0. The first term on the top represents the pure flexural buckling about y-axis. The second term is representing the flexural torsional buckling, also known as FTB. So when we simplify this further, we get an equation of Pcr, which is Pcr equal to P gamma plus Px divided by 2 into 1 minus x0 square by R0 square into bracket open 1 minus root of 1 minus 4 Px into P gamma into 1 minus x0 by R0 the whole square divided by P gamma plus Px the whole square, bracket close. This equation is very similar to the section 4 of AISC 360 highlighted in the right hand side. Here H is defined as 1 minus x0 square by R0 square and Py equal to Pz. The above equation contains Px because x-axis is considered as the axis of symmetry, whereas the ones that are highlighted where y-axis is considered the axis of symmetry. Let us look at the failure modes of the columns and the beams discussed so far. So in columns, the columns can fail by yielding, it can fail by flexural buckling about minor axis, it can fail by flexural buckling about major axis, it can fail by flexural torsional buckling, whereas in beams, it can fail by yielding or it can fail by lateral torsional buckling. Now these modes of buckling represents global buckling mode which happens at the member level. As you can see from the figure here, the cross sections are made of elements. You can see at the top flange, which is an element. We can see the web is also an element, the bottom flange is also an element. The steel sections can buckle locally due to high slenderness ratios. The slenderness here is defined as the width of the plate divided by the thickness of the plate. So, it can be the width of the flange, which is B, and divided by the thickness of the flange, T sub F, or it can be the depth of the web divided by the thickness of the web, which is D by TW. And this happens within the elements under compression, and hence it is called local buckling, which happens at the element level. So, when you apply a load here, as you can see on the right hand side, the member stays stable. The elements of the member buckle locally, as you can see. A blown up view is shown here of the local buckling region, where you can see a sinusoidal curve that is happening both at the flanges as well as at the web. And if you look at the boundary condition for this one, the one represents the free edge, which is basically free because it is an unstiffened lip, and the number 2 represents the junction between the flange and the web. So, this is considered as a simply supported edge. And the half sine wave buckling is shown here in the picture. The local buckling of elements reduces the load carrying capacity of the member. It is essential to understand local buckling behavior of elements in a cross section. With this one, we have completed both the beams and the columns for member buckling. We will talk more about element buckling, which is local buckling, in the next class. Thank you very much.